Morning, all of you. In this lecture, we are going to discuss about economic load dispatch. So already we have discussed about many topics, which is based on your economic load dispatch. And in this lecture, we are going to discuss that what is your economic and what do you understand by economic load dispatch and which kind of methods we are using for economic load dispatch. So as we discussed that in power generation process, economic load dispatch is very important because it economic load dispatch is depending on the economy of your generation and uh, the generation cost is also depend on your economic load dispatch and how economically we can improve our power generation and power supply. So this is about your power generation process. So learning objective of this lecture is to understand the concept of economic load dispatch and learning outcome student will be able to understand the concept of economic load dispatch. So after this lecture I'm expecting from student that student will be able to understand easily that what is your economic load dispatch and how we can use different methods for economic load dispatch. So these are the content of this lecture. The contents of this lecture is type of power plant, requirement of power plant design, terms and definitions, tariff and requirement of a tariff, economics of power generation, and power plant site selection and problems. So first we will discuss about that how many power plants we have and what are the different type of power plants. So power plants can be divided into different divided into different parts depending upon the different criteria. So, based upon the various factors, the power plant are classified as follows on the basis of fuel use. So, first we will discuss that if you consider your fuel, so according to your fuel, how can you divide power plants? So, according to fuel, you can divide power plants. So that one is your first is your condensing power plant, non-condensing power plant, diesel power plant, nuclear power plant, hydroelectric power plant, gas turbine power plant. So you can see in this, uh, different type of power plant that the name is depending upon the fuel, which kind of fuel you are using in power plant. So one is your diesel power plant, nuclear power plant. So in diesel power plant, uh, you are using your diesel. In nuclear power plant, you are using uranium. Hydroelectric power plant, you are using water. And gas turbine power plant, you are using gas. Now, the question is, what is the difference between condensing and non-condensing power plant? So, to understand the concept of condensing and non-condensing, condensing means when you are using condensing process like thermal power plant, you are using water to convert into steam, and then steam is again converted into water, and that steam is used to generate the electricity. Okay? So that is your condensing power plant. Now, non-condensing power plant depends upon totally on fuel like diesel, nuclear, hydro, electric, and gas turbine, in which you are not heating any kind of water, or you are not making steam to generate the electricity. So, on the basis of fuel, we can divide these power plants. Now, the second point is on the basis of nature of load. So, on the basis of nature of load, you can divide the power plants into two parts. One is your base load power plant, and another one is your peak load. So, what is your base load power plant? So, we will discuss it later. But according to the load, base load basically the load which remain constant in the whole day. Okay, like you can say that minimum this much load is required. Okay, peak load it comes one or two time in a day. Okay, so that is your peak load power plant. So we will discuss it in our next lecture. Now, if we talk about on the basis of location, so on the basis of location, you can divide it down into two parts. One is your central power plant, and another one is your isolated power plant. And on the basis of service rendered, you can divide it that stationary power plant and locomotive power plant. So these are the four categories in which we can divide it the power plants. Now another one is your requirement of power design, plant design. So the factor to be kept in view while designing a power station are as follows. So if you are designing a power plant, so you have to consider many points that how can we run power plant, how can we run economically this power plant. So there are a few points which you have to or we must consider when you are designing a power plant. So the factor to be kept in view while designing a power station are as follows. So one is your economy of expenditure. So basically, economic is related to money. Okay, and it can be divided into two parts in power plants. One is your capital cost, and another one is your operating and maintenance. So, what is capital cost? Capital cost means if you want to set up a power plant, you have to purchase land, you have to purchase equipments, and you have to do some investment, insurance, and many other things. So when you are constructing or settling a power plant, so the cost which is you are going to expend or you are going to you know uh, uh, for purchase the land and other things, so that is your comes into the category of capital cost. Okay, so in operating cost, suppose you have set up a power plant. Now you want to run this power plant. So there are many things which we have to consider when you are operating a power plant. For example, maintenance of equipment, the fuel cost, and you know the money for the workers who are working in power plant, salaries of those workers. So these comes into the operating and maintenance. So the economy can be divided into two parts. One is your capital cost, another one is your operating and maintenance. Next one is your safety or power. Safety of the plant personnel, like the person who are working in power plant. So there are many chances to get injured or to happening something bad with the workers which are working in power plant. So first we have to look after the safety or of those people who are working in power plant. Okay, next is your reliability. So what do you understand by reliability? Reliability means that uh, you can say reliability means you are getting the electricity reliable. Electricity reliable means that when you required electricity, you are getting the electricity. Okay, if you are if you are you know quality. So there are one point is your quality. You are getting quality uh, quality in electricity or in power plant. So that must be reliable. Whenever you required, you are getting electricity. Suppose you required electricity and you are not getting electricity, so the power plant is not reliable. And the second thing that you are getting the electricity at as much as cheaper cost. Okay, so these points come into the point which is a reliability. So we will discuss it in it later in no, in the next lecture. What is efficiency? Efficiency means suppose you are uh, how much input you are giving to a power plant and how much output you are getting. So which in the input you are giving that must be equal to your output. So the efficiency of a power plant will be 100%, but it is not possible in this is only possible in ideal case. So maximum efficiency should be there for a power plant. Easy of maintenance. The power plant ease of maintenance means that how can you maintain a power plant? So good working condition. It must be into a good working condition. And the most important point that the transmission loss should be minimum, because if your transmission loss are maximum, then the electricity cost will be very. So these are the few points which must be considered when you are running or setting up a power. Next is your terms and conditions. So, in terms of condition, there are few points we will discuss. So, one is your connecting load. So, what is your connecting load? Obviously, the load which is connected to the power plant, that is your connecting load. So, it is the sum of ratings in kilowatts of equipment installed in the consumer's premises. So, for example, we can take if a consumer has connection for four lamps of 60 watt each. Okay. Suppose I'm a consumer, I'm having four lamps at my home, and each lamp is having a rating of 60 watts. So total load is becoming your by 60 into 4, that is your 240. And I am having one point that is your 500 watt. So 240 plus 500 watt, and I am using a one radio consuming. I have one radio that is consuming by 60 watts. So total load becoming 4 into 60 plus 500 plus 60 is equal to 800. Okay. So this is your connecting. Now next point is your demand factor. So it is defined as the ratio of maximum demand to the connecting load. So demand factor is equal to maximum demand upon connecting load. Now next point is your load factor. So it is defined as the ratio of average load to the maximum demand load factor, and demand factor always less than the unity. Why it is? Because you can see the formula of load factor. So load factor is equal to average load upon maximum demand. So obviously the maximum demand is always greater than your average load. So that's why the load factor is always less than unity. So you can see from the diagram that the power demand is given in you know, uh, in kilowatt on the y-axis, and the power demand is given on x-axis. Load time is given on x-axis. So you can see that, and this particular time the demand is this at this point. After this, the demand is decreasing. After few time, it is gradually increasing. That at this point. After this, it is also decreasing. After this, it is increasing. So this is your maximum demand. That is your average load, and this is your base load. Base load means the line is constant. So this is your minimum load, which is all the time you require. Okay. So this is your base load. So this is your load curve. Next point is your plant capacity factor. So what is your plant capacity factor? Plant capacity factor is that is defined as the rate of actual energy that could have been produced during the same period. So this is our demand factor. Okay. Now, what is the difference between load factor, plant capacity factor, and other things? To picture. So most of the loads, 80% in electrical distribution power system, are inductive in nature, and hence they have low power factor, which is highly undesirable. So low power factor causes an increase in reactive current, so resulting in additional losses of active power in all elements of power system. So it is important to have power factor as close to unity as possible. So leading power factor is also undesirable for power system. Okay. So power factor must be nearest to 1. So we always try to keep our power factor nearest to 1. But there will always be some low power factor just because of your inductive load which is connected from the consumer side. Now we come to the point, what is power factor? So power factor is the angle cos phi of the angle cosine of the angle between voltage and current. So this is your voltage waveform and this is your current waveform, and you can easily understand that the difference between V and I is your by angle theta. So this is your power factor. Okay. So if the circuit is inductive, the current lags behind the voltage by angle theta, and power factor is referred to as lagging power factor. So now is it clear to you that what is your lagging power factor? Okay. Now next come to the point is your leading power factor. So if the circuit have capacitor and resistance, then the power factor will be your leading power factor. And from this diagram, you can see that the current is leading by the voltage by of angle theta. If you want to draw the phasor diagram of this capacitive load, then you have to take the voltage on x-axis, and this is your imaginary axis, and the current which is leading by an angle theta. So power factor, if circuit is resistive, both current and voltage are in phase with each other, and power factor is referred as unity. Okay. If both voltage, and from this diagram you can see, if both voltage and current are in phase, then the power factor will be 0, and uh, power factor angle will be 0. And if you draw the phasor diagram of this circuit, you can see the voltage and current are in same phase, so the angle between the voltage and current is 0. Now this is your power factor triangle. This is your working power, which is represented by kilowatt. This is your apparent power, which is represented by kilovolt amperes. And this is the angle between kilowatt and kilowatt volt amperes. And this is your reactive power, which is in kVA. So apparent power kVA, and this is your working power in kilowatt. The angle between these two is represented by theta. Okay. So x-axis, on x-axis you can represent your active power, y-axis is representing your reactive power. Now apparent power in AC circuit has two components, active or working power and reactive power. From trigonometric relation we can easily find out the cos theta, which is equal to working power upon apparent power, which is equal to kilowatt upon kilovolt amperes. So the power factor of a circuit may also be defined as the ratio of active power to the apparent power. For leading currents, the power triangle becomes reversed. So now the power factor can be defined in one of the following three ways. Power factor is equal to cos theta, which is equal to cosine angle between V and I. Power factor is equal to cos theta, which is equal to resistance upon impedance. And power factor is equal to cos theta, which is equal to active power upon apparent power. So Let us assume a circuit having current of 10 ampere. We can easily understand by taking one example. Let us assume that a circuit having 10 ampere at a voltage of 200 volt. Okay, the current is given your 10 ampere and the voltage of the circuit is your 200 volt, and the power factor is lagging, which is your 0.8. So now you have to calculate your apparent power and active power and reactive power. So by the formula of apparent power, S is equal to VI, you can easily calculate uh, your apparent power, which is equal to 200 multiplied by 10, which is equal to 2000 volt amperes, is equal to 2 kilovolt amperes. Next is your VI cos phi, and VI cos phi is equal to uh, 200 into 10, and cos phi is given 0.8. So your active power is 1.6 kilowatt, and Q is equal to VI sin phi. So your reactive power is 200 into 10 into 0.6, which is equal to 1.2 kilovolt ampere reactive. So the circuit receives an apparent power of 2 kilovolt ampere and is able to convert only 1.6 kilowatt into working or active power. And the reactive power 1.2 kilovolt ampere neither consumed nor it is does any useful work. So it flows back and forth in both direction periodically. So by this example, I think you are clear that what is your active power, what is your reactive power, and what is your apparent power. Now, let's come to the next point, that different type of electrical loads have different power factors according to its nature. If your load is lightly loaded inductor motors, then it has very low power factor, which is 0.20 lagging. If your motor is fully loaded, then it will have 0.80 lagging power factor. If your equipment is connected neon lightning equipment, it has 0.30 to 0.70 lagging power factor. If the equipment is your lamps, then it will have 1.0 unity power factor. So all types of resistance heating devices have one one unity power factor. So what are the causes of low power factor? So most loads, 80% in electrical distribution system, is in inductive in nature. So the main cause of low power factor is your inductive. So inductive load responsible for low power factor, for example, most of AC motors are induction type motors. It may be your single phase motor or it may be your three phase motor. So at light load, these motors work at extremely low power factor. So it has power factor from 0.2 to 0.3 and rises to 0.8 to 0.9 at full load. And arc lamps, electric discharge lamps, welding equipments, and industrial heating furnace operated at low lagging power factor. So transformer draws a magnetizing current from the supply. At normal load, this current does not affect the power factor, but they draws larger amount of magnetizing current at light load, causes low primary current power factor. So these are the few examples which is responsible for low power factor. But the option is that you can't ignore these motors and lamps and some other equipment because which are necessary for our daily life. So the second option is that you have to improve the power factor by some other methods. So what are the demerits of low power factor? How it can affect your system? So low power factor resulting the following disadvantages. One is your at larger kVR ratings. Okay, if your power factor is low, then the equipment which you are using in your switch gear in switch cards, switch gears, for example, alternator, transformers, it always required high power rating. So electrical machines are always rated in kVA, and kVA rating of any equipment varies inversely with the power factor. If your power factor is low, then your kVA rating of equipment will be high. So therefore, low power factor increases the kVA rating. As a result, kVA rating making the equipment larger and expensive. Now, next is your cos phi, cos theta. This is your power factor, which can be represented by the formula working power upon apparent power. So working power is in your kilowatt and apparent power is your kilovolt amperes. And the second is your greater conductor size. If your power factor is low, then you always actually, if your power factor is low, then it will draw on the high current, and if it is drawing high current, then you require the conductor, greater size conductor. So to transmit a fixed amount of power at constant voltage, the conductor will have to carry more current at low power factor. So it can be represented or it can be understood by this formula that the current is equal to P upon root 3 BL cos phi. If cos phi is your high, if cos phi is your low, then the current will be high and you need larger size of conductor. If this is high, then it will draw low current and you need lower size of conductor. Okay. Now it demerits of power factor, which is continued. So it has large copper losses because if low power factor, then the current will be high. If current is high, then the copper loss which is represented by I square R will be high. So the large amount of current at low power factor causes more I square R losses in all the elements of the system. Now, poor voltage regulation. It required larger amount of current which is produced large voltage drop in alternators, transformers, transmission lines and distributors, this resulting in poor voltage regulation. Now, it is paid extra utility charges. If your system is operating at low power factor, then it is very uneconomical and you have to pay large charges or extra charges for utility. So the system operated at low power factor is uneconomical from suppliers' point of view, and suppliers usually takes extra charges from consumers who operated their load at low power factor. So it is very important and it is must needed to correct our power factor. So let's come to the point that what are the procedure by which we can correct the power factor. So everyone knows that these are the components or electrical components, which is a resistor, inductor, capacitor and synchronous condenser. So the process of supplying reactive power lagging or leading to bring the power factor closer to unity is known as power factor correction. So this can be done by the following equipments. It may be your resistor, it may be your inductor, it may be your capacitor, and it may be your synchronous condenser. So power factor correction the required these equipment. For example, the capacitor draws a leading current and neutralizes the lagging reactive components. You can see that it is from the diagram that the for this current I, the power factor is phi 1. For I dash current, the power factor angle is your phi 2. So by applying capacitor, you can see that this is your inductive load. You can connect a capacitor in parallel with this. That you can see that before applying the capacitor, the power factor was your phi 1. After applying the capacitor, the angle reduces from phi 1 to phi 2. So the capacitor draws a leading current and neutralizes the lagging reactive component to the load current. This raises the power factor. And correct amount of capacitance must be used. Otherwise, power factor goes from lagging to leading, which is also undesired condition. Now, how can we correct the power factor? You can easily understand from this diagram that in the case of inductance, uh, at this point the energy is storing and at this point energy is releasing. Okay. But when you talk about your capacitor, at the same time when inductor is storing the energy, the capacitor is releasing the energy. At the same time when it is storing the energy, the inductor is releasing the energy. So by this diagram, we can easily understand that how capacitor can be improve or correct our power factor. So power factor correction static by using static capacitor. For example, that assume a circuit, it is shown in figure A, in which pure resistive load of 120 kilowatt is connected with 600-volt generator. Okay, supplying 200 ampere as shown. So first calculate its apparent active and reactive power because load is your resistive. So S is equal to P because cos phi is equal to 0. In this case, the apparent power will be equal to your active power and the reactive power will be 0. Right? Now, the power factor is equal to 1. Now, lagging inductive load is added at shown in figure with the same 600-volt generator. So you have connected now one inductive load over here. So you can see that P is equal to 120 kilowatt and QL is equal to 160 kVAr. Okay. So it will draw some current, this inductive load. And you can see when you connect inductive load in parallel with this resistance, then you can see that the active power is remaining same, but your reactive power is increased and it will be your 160 kVAr, which is 0 over here. Okay. So even though it is supplying same 120 kilowatt to the load in both the cases, but current exceeds from 200 ampere to 333 amperes. Okay. In this case, the current is increasing. You can see, you can compare these two diagrams that the current drawn here is 200 ampere and the current drawn in this case is 333 ampere, but the active power is remaining same in both the diagrams. Okay. So now we are determining the value of capacitor placed in parallel with the load to raise the power factor is equal to 1. So calculating the capacitor, first we have to calculate the reactive power due to this capacitor, which is equal to V square upon XC. So V is your 600 volt and the reactive power is your, you want to, compensate this amount of power. So XC is equal to V square upon XC, which is equal to 160 kVAr. And you are getting 2.25 ohm of this capacitor, sorry, reactance. And now by using this reactance, you can easily calculate the capacitor value. You know, C is equal to 1 upon 2 pi f xc, and 1 is equal to 2 into 3.14 into 52.25, which is equal to 1415 microfarad. So this much of rating capacitor you required to compensate this kind of this much of your reactive power. Okay, so you have to connect the capacitor of 1415 microfarad. Okay, so this is the example by which you can correct the power factor. The next example is that power factor correction by synchronous condenser. So you know what is synchronous condenser? We have already seen in our previous slide that a overexcited synchronous motor running on no load is known as synchronous condenser. Okay. If you increase the field excitation of synchronous motor, it will improve the power factor from lagging to leading by operating in overexcitation mode. And when synchronous machine is connected in parallel with the supply, it takes the leading current, which partially neutralizes the lagging reactive component of the load. So by using this synchronous condenser, you can also improve the power factor. Now, what is synchronous condenser? This is an overexcited synchronous machine running on no load is known as synchronous condenser. The overexcited synchronous motor takes leading current and behave like a capacitor. When it is connected across supply, it draws leading current and partially or fully compensate the lagging reactive component of load current. So which results improve the power factor. In this way, power factor can be improved to unity even. So synchronous condensers are usually used where a large quantity of corrective kVAR is to be required. So this is the importance of synchronous condenser by which you can improve the power factor. Now, what are the advantages of this synchronous condenser? So by varying the field excitation of synchronous machine, you can easily improve the power factor to a finer value. And synchronous condenser can withstand overloads for shorter duration. If your load is over, then this synchronous condenser also can withstand. Now, what are the disadvantages? Disadvantage is that the cost is higher than the static capacitor of same size for above 500 kVA. The maintenance and operation cost of synchronous condenser is also high, and the considerable losses in rotating parts of synchronous condenser is also high. Lower efficiency compared to static capacitor is also high, which is 97%. It produces noise during operation. Synchronous condenser is not self-starting. You have to start it. Okay. So hence it required auxiliary supply or auxiliary equipments to start the synchronous condenser. And there is a chance to fall synchronous condenser out of synchronism, which leads interruption of supply. Okay. Now we can use three-phase advancer. So the phase advancer is a simple AC exciters. It can be mounted on the same shaft of the main motor, and it supplies exciting ampere turns to the motor circuit at slip frequency. Then it provides flux, which results improve the power factor. It further increases the excitation the power factor goes to lead like overexcited synchronous motor. So what are the advantages of using this? The lagging power factor kVAR drawn by the induction motor can be considerably reduced by supplying leading ampere turns at slip frequency. And the phase advancer is conveniently employed where the use of synchronous condenser is not suitable. And disadvantage is that they are not economical for motors below 150 kilowatt. So you can see from this diagram that This is the power supply which is connected to the load, and the reactive active power is your 8000 kilowatt, reactive power is your 6000 kVAR, and this is your apparent power which is your 10,000 kVA. So the power factor, if you want to calculate by the formula P by S, so P is your 8000, S is your 10,000, the power is your 80%. And if you want to improve the power factor by using capacitor, so you can use the capacitor of 4000 kVAR, and you can see that after using these capacitor, the kVAR rating is becoming down, which is coming from 6000 to 2000 kVAR, and the power factor is becoming your 97%, which is kilowatt upon kVA. Okay. So what are the advantages of power factor correction? Obviously, by correcting the power factor, you can reduce the rating of alternator, transformer, and switchgear, which can be decreased. The size of the conductor decreases, the power loss in the system decreases, and it is better voltage regulation. It will increase the system efficiency, and there is no penalty if power factor tariff is using, and overall cost decreases. So this is all about your power factor and power factor correction method. So I want to summarize this lecture that for power factor is always represented by cos phi, where phi is the angle between voltage and current. If your load is resistive, the power factor will be maximum, because in the case of resistance, the voltage and current will be in the same phase. So phi will be 0 and cos phi will be 1. So in the case of resistive load, your power factor will be maximum. If your load is inductive, there will be some power factor, and the power will be P is equal to VI cos phi, and the reactive power will be Q is equal to VI sin phi, and apparent power will be S is equal to VI. Okay. Now, if there are some disadvantages, there are disadvantages which require to improve your power factor. So one of them is that the rating of equipment which you are using will be high if your power factor is low. And the second disadvantage, that it consume high current, then you require larger conductor, which is not good for your in the point of view of economics. And the generation cost will also be high, and your tariff is based on your power factor, and if your power factor is low, then you have to charge some penalty. So it is needed to improve your power factor by using some methods, in which we discussed about that for correction of power factor, you can use capacitor, condensers, and AC exciters. And these all have some advantages and disadvantages. So first you have to choose a perfect method which can improve your power factor, and for choosing the power factor correction methods, you required a proper size of capacitor and proper place where you can place these capacitor to improve the power factor. Okay, so this is all about our lecture, and there are some questions which is based on this lecture. So first question is that the installation of capacitor at suitable locations and of optimum size in a distribution system results in. So it will improve voltage regulation, reduction in distribution power loss, reduction of kVA rating of distribution transformer, and you can see that it will improve voltage regulation. So three are the correct option. So C is the option for this question. Now second question is Low power factor is usually not due to discharge lamps, incandescent lamp, arc lamps, induction furnace. B is the right option because it is almost your resistive load. So this is not responsible for your low power factor. Next is your the primary reason for low power factor is owing to installation of synchronous motors, DC motor, induction motor, and commutator motor. So C is the right answer, that induction motor is responsible primary reason for low power factor. Now, medium size induction motor will operate at maximum power factor while operating at full load, 50% of full load, 25% of full load, and any load. So option A is the right answer, that the induction motor will operate full load to maximum power factor. Next question is, low power factor has a drawback of increased transmission and distribution losses, poor voltage regulation, high cost of equipment for given load, and all of the above. So D is the right answer, that the low power factor has a drawback. It increases transmission and distribution losses. It is responsible for your poor voltage regulation, and it is a high cost of equipment. It required high cost of equipment for given load. Okay, so D is the right answer for that. Next question is, the low power factor of an industrial plant is uneconomical for electric supply utility only, owner of the plant only. Actually, it is uneconomical for both electrical supply utility and owner. So C is the right answer for this question. Now, next question is, for a consumer, the most economical power factor is usually 0.25 to 0.5 lagging, 0.25 to 0.5 leading, 0.85 to 0.95 lagging, and 0.85 to 0.95 leading. So C is the right answer. Next question is that the power factor can be improved by using static capacitors, synchronous condenser, phase advancer, and all of the above. So D is the right answer for that. That the power factor can be improved by all of the above. You can use a static capacitor also. You can use synchronous condenser. You can use phase advancer, and all of the above. So all of the above is your right answer. Now, static capacitors are rated in terms of kVAR, kilowatt, kVA, kilowatt hour. So static capacitor is always rated in terms of kVAR. So this is all about your this lecture. If you have any questions, any doubts, you can ask in our next lecture. So this is all about your power factor, and I hope that you are now able to understand that what is your power factor and what are the different methods which can be used for power factor. Thank you.